In this class, I will explain about one important equation called continuity equation in a three-dimensional Cartesian coordinates for a fluid flow. So this actually gives a relationship between the velocity components in a fluid flow. Of course, if it is an unsteady flow, it relates the time component also. So to understand this continuity equation, it is derived based on one important law called law of conservation of mass. You have learned three important fundamental laws in mechanics. One is law of conservation of mass, that is, mass can neither be created nor destroyed, in simple words. Second one is the law of conservation of energy, and the third one is the law of conservation of momentum. So same laws they hold good in the case of fluids also. So here this continuity equation is derived based on the law of conservation of mass. So it is refined in this way. Rate of change of mass in fixed region in a fluid flow is nothing but is equal to difference in the rate of mass entering and leaving the fixed region. So this is how we can define in the case of a fluid flow. Because fluids only can flow, solids cannot flow. So they only move from one point to another point. Here the entire mass of the fluid it will be flowing. Now here, to understand this wordings, we will consider a fluid flow, maybe a pipe flow or a channel flow. In that flow, I will take a fixed mass like this. This fixed mass is mf. M stands for mass, F stands for fixed region, which has got a mass, fixed mass mf. So during the flow of a fluid in this region, you will be having some mass inflow to this fixed region, and also certain amount of mass outflows also. So both inflow and outflow will be there from this fixed mass. So inflow you take it as mass inflow, you take it as mi, mass outflow you take it as mu. Now there are three important terms here, mi, mu and mf. Now according to this statement, rate of change of mass in fixed region in a fluid flow, that means it is with respect to rate, means it is always with respect to time. Please keep that in mind. So the meaning of this is in mathematical form, we can write as dmf by dt. This should be equal to difference in the rate of mass entering and leaving the fixed region. So mass inflow is mi, mass outflow is mo. Difference we have to take. Maybe mi may be more than mo or mi may be less than mo. That doesn't matter. That's why the word difference is taken. So the difference symbol is written like this. So mathematically we can write the RHS term as d by dt of mi difference mo. So if mi is greater than mo, you have to take mi minus mo. If mi is less than mo, we have to take mo minus mi. So higher minus lower value we have to take. That is meaning of that. And you know that in the case of fluids, mass of a fluid m can be obtained by multiplying the specific mass or the mass density rho by the corresponding volume. So that is rho into V gives the value of m. That is from the basic definition of mass density. Now to understand the continuity equation, I will consider a small element of a fluid in the flow. So that element has got a very small volume. So I will take a cuboidal element whose volume is defined as dx into dy into dz. So I have taken the coordinates like this. The volume of this fluid element, now it is dx into dy into dz. So now to this element, flow will be there from all the three directions. So in the x direction, this is the inflow, this is the outflow. In y direction, this is the inflow, this is the outflow. In z direction, this is the inflow, this is the outflow. Now I have shown the arrows. So now here, mix means it is the mass of the fluid entering in x direction to this fixed region. MOX means mass of the fluid leaving, O means outflow, I means inflow, leaving the fluid in leaving the element in x direction. MIY means it is the mass of the fluid entering in y direction. MOY means mass of the fluid leaving in y direction. MIZ means mass of the fluid entering in z direction. MOZ means mass of the fluid leaving in z direction. So totally we have 6 quantities here in a 3-dimensional flow. Now using this concept, if you adopt this equation, if you write in this form and if you simplify in all the 3 directions x, y, z, finally we are going to get the continuity equation in this form. So here you can write the continuity equation in different forms based on whether it is 3-dimensional or 2-dimensional or 1-dimensional, whether it is steady or unsteady, whether it is compressible or incompressible. So depending on the type of flow, we can write the continuity equation in different forms. So I have written here of course some 4 different forms which is important for us. The first form is 3-dimensional continuity equation for unsteady compressible flow. So this is general equation. Considering all the terms, we can write the continuity equation in this fashion. Here you can observe that is, in the case of a compressible flow, mass density is not a constant. It varies from time to time. So then another thing is unsteady means the other properties, that is velocity components, they also vary with respect to both space and time. So in such a case, we can write this continuity equation in this form, because rho is not a constant, we cannot take rho outside this. So here u, v, w, they are all functions of x, y, z, and rho is a function of t. Therefore, the continuity equation will be of this form: rho by dou x of rho u plus dou by dou I of rho v plus dou by dou z of rho w plus dou rho by dou t. So this term gives that it is unsteady. It is unsteady. That means rho is not constant, as well as it is compressible because rho depends on the time. Now the second form is 3-dimensional continuity equation for steady incompressible flow. In the case of steady incompressible flow, what happens? This rho becomes a constant. This is the important thing. Rho is a constant. It won't vary with respect to time. Since rho becomes a constant, so dou rho by dou t becomes 0. Rho is constant with respect to time, its derivative will be 0. This term will not be there. And coming to these terms, here also, since rho is constant, you can take rho outside. So if you take rho outside, it becomes rho into dou u by dou x plus dou v by dou y plus dou w by dou z. Anyway, this term becomes 0 is equal to 0. Then that rho also can be removed, because rho into something is equal to 0 means rho can be removed. So finally you are going to get only this. So this is the most common equation we are going to use for water. So because water is incompressible, normally it becomes a steady flow because rho is constant for water. It won't vary much. Whereas in the case of other gases and all, this equation cannot be used there, because gases are compressible fluids. We have to use this equation. For water, better you remember this equation. Very simple equation: dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Can be used mainly in the case of water, which we civil engineers are dealing with. We are not worried about gases. Now coming to 2-dimensional. So from 3-dimensional, you can reduce you can derive the 2-dimensional continuity equation. Only thing is, in case of 2-dimensional, only x and y will be there, z will not be there. So in this equation, the third term will vanish. W is not there, z is not there. So then it becomes a steady, incompressible only, but it is 2-dimensional. So this is another equation which we are using for 2-dimensional flow. And the most important for practical analysis, we take this 1-dimensional steady incompressible flow. For in that case, v is a function of only x. So here you can see v is a function of all the 3 space coordinates as well as time. Here only space coordinates. So here x and y only two space coordinates, here only x. So this can be further simplified and written for analyzing practical problems as q is equal to a into b. So this is the one dimensional continuity equation which we are going to use in most of the cases. So here this q, as already told, it is defined as the discharge as the rate of flow, which is expressed in meter cube per second. That is the volume of fluid that is flowing per unit time. So volume meter cube, time is second. So that is known as discharge rate of flow. This is the SI unit, meter cube per second. Then A is nothing but the cross-sectional area of flow. If it is a circular pipe, so then you have to take the area of that circular pipe as d is the diameter, pi d square by 4 becomes the area. If it is other than that, in the case of channels, it can be rectangular, triangular, or it can be trapezoidal. So we have to take the area of that particular shape. Whereas in case of pipe, it is always pi d square by 4. That is the cross-section area. If the pipe is flowing full, then it is pi d square by 4. If the pipe is flowing half, only this much if it is flowing. Sometimes partial flow also may be there in the pipes. So in that case, we have to take the half area. So whatever area of flow is there, so then it becomes pi d square by 8. So you should be very careful. If it is flowing full, then it is pi d square by 4. If it is flowing half full, then it is pi d square by 8. Half of that area of the semicircle we have to take. Then v is the velocity of flow, which is given by meter per second. So when you multiply cross-section area of flow with velocity of flow, you are going to get the rate of flow or the discharge in general. Now I will take an example like this. It's a tapering pipe which I have explained in the last lecture. So with diameters d1 and d2 are the two ends. If q is constant here, so this q is constant. So please note that q is constant here. Q constant means it is a case of a steady flow. That is it. So if q is constant, we know that q is equal to a into b. So here also q is same. Here also q is same. So at both the points, both the sections, you have the same discharge. So here q is a1 v1, here q is a2 v2. So where a1 is pi d1 square by 4, a2 is pi d2 square by 4. That means if you want the velocity here, v1 is the velocity here, v2 is the velocity here, they are different because a1 and a2 are different. Even though q is same, since a1 and a2 are different, v1 and v2 will be different. So that is why it is the case of a non-uniform flow because velocity changes over a length. So we can find out the velocities by knowing the discharge on the area using this formula. v1 is q by a1, v2 is q by a2. So that means in general, whatever may be the number of sections we are going to consider. Here I have taken only two sections, 1 and 2. It can be any number. At all the sections, if the discharge is same, q is same, then you can write this equation. This is the continuity equation in general. Q is equal to a1 v1 is equal to a2 v2 is equal to a3 v3, like that you can take. So this q is expressed in meter cube per second, or another word is it is cubic. Meter cube per second is also called as cubic. And your conversion is sometimes they are giving liters per liters. So you know that 1 meter cube is nothing but 1000 liters. You have to keep it in mind because whenever they give you the LPS means liters per second, you should be in a position to convert it into meter cube per second because before substituting in the formula, all the units should be in SI units. SI unit of discharge is meter cube per second. So if they give 500 liters per second, then you have to take it as 0.5 meter cube per second. Okay, like if they give 2000 liters per second as the flow, then you have to take it as 2 meter cube per second. So 1 meter cube is 1000 liters. That is the conversion, that is the conversion you should know. Now I will take an example, simple example. So here in this example, there are two pipes connected together, and the flow takes place in a common pipe. So I will take this as first pipe, this as second pipe, this as the third pipe. So corresponding notations I will give. Velocity in this pipe v1, velocity in this pipe v2, velocity in this pipe v3. Diameter of this pipe d1, 0.15 meter or 150 mm. So if they give in millimeters or centimeters, first of all you convert that into meters because everything should be in meters, meter square, meter cube and seconds. You should be very careful there. So second pipe diameter is 200 mm, that is 0.2 meter. Third pipe diameter is 300 mm, that is 0.3 meter. Now in this question, he has given the velocity in this pipe, he has asked the velocity in the common pipe, that is third pipe. So discharge from these two pipes, they will combine here and combined discharge will flow here. So normally this type of pipe network you can observe in drainage. So in drainage, so these two are the secondary pipes, they will connect to a common primary pipe. So discharge in this pipe will be equal to discharge in this pipe plus discharge in this pipe. So in this case it is Q3 is equal to Q1 plus Q2. So by using that equation, this is the continuity equation here, you can find the velocity in the third pipe. Very simple problem. So Q3 can be written as A3 into V3 because Q is equal to A into V, where A3 is the area of this pipe. Q1 is A1 V1, where A1 is the area of this pipe. Q2 is A2 V2, where A2 is the area of this pipe. He has given velocity in the first pipe 2 meter per second, velocity in the second pipe 3 meter per second, velocity in the third pipe, that is the common pipe, is unknown. Now get the values of A1, A2, A3 by using the formula pi d1 square by 4, pi d2 square by 4, pi d3 square by 4. D1 is 0.15, D2 is 0.2, D3 is 0.3. By substituting and simplifying, you will get the corresponding values. Substitute and simplify in those values in this equation. For the only unknown is V3, that you can get as 1.833 meter per second. So that is how you can find the velocity in any pipe by knowing the velocities and the areas of all the other pipes by using continuity equation. So this is a very important equation, continuity equation, which is the basis for analyzing certain fluid flow problems in future.